Now that we've talked about fluid statics, the last thing we're going to talk about relating to fluids is not fluids that are at rest, but fluids that are in motion. This is a huge topic with research groups everywhere doing giant computer simulations and everything. We're not going to go into a lot of detail in this. We're going to use two equations to do fluid dynamics. But these are applicable in a lot of cases and in some important medical cases too. So the analysis that we're going to do is going to apply to fluids with the following characteristics. So this analysis applies to fluids that, let's say, that are, well, okay. So there are four things here. The first one is that the flow of the fluid has to be steady. That means that it doesn't change over time. So if you somehow were able to measure the velocity of a single location in the fluid flow as time went by, that point would always have the same velocity. Fluid would always be moving in the same direction at the same speed every time it came through that point. The second thing is there aren't going to be any viscous effects. So viscosity, you can think of as like water has a low viscosity, syrup has a high viscosity, and we're only going to be analyzing flows where that is not significant in the way the fluid behaves. We're going to be talking about water a lot. Third, it has to be incompressible. That means that the density doesn't change. This is almost always applicable for liquids. It's not as applicable for gases. You know that if you fill a syringe with air, you can press that syringe down, and that's compressing the air, changing the density. You can't do that with water. So this almost always holds for liquids. You have to have big temperature changes in order to have a major change in density for a liquid. But it also holds for gases if the temperature and pressure don't change much. And then the fourth, the last one, I'm just putting this down, but it has to be irrotational. So we're just talking about flows that don't have vortexes of spinning whirlpool kind of stuff in it. So in practice, what do these four things mean? It means you have to have low turbulence. So like a river that's moving really quickly through rocks, you get a lot of bubbles, you get a lot of you get a lot of sort of unpredictable effects near barriers. That's turbulence. Whereas if you just if you get water slowly moving down a chute, you don't see a lot of these effects. That's non-turbulent flow. So this only applies when there's not much turbulence. And like I said up above, this always applies to liquids. But if you're going to use this with gases, you have to be careful. So be careful using this with gases. The greatest relevance of this stuff in medicine, there are really two main areas. The first is blood flow through blood vessels. And the second one that involves gases, so again, you have to be careful with this. The equations I'm introducing aren't always going to apply, but this approach is used to study airflow through lung airways too. And I'm just going to give you two equations. And most of the time, these two equations are going to be used together. So every problem is going to use both of these two equations. The first one is called the continuity equation. And the second one is called the Bernoulli equation. So I'm going to start with the continuity equation, then I'll go to the Bernoulli equation and give you a couple of examples of how these are used. Okay, so the first thing we're going to talk about is the continuity equation. And what this says, as far as understanding it, is when fluid flows through a pipe or a tube or whatever. So let's say that fluid flows through a pipe. If the cross-sectional area of the pipe changes, the speed of the fluid flow has to change also. So the speed of the flow also changes to keep the volumetric flow rate constant. Okay, so if you think about the fact that we're requiring these fluids to be incompressible, what that says is that every point through a pipe, so let's say that this is a cross-section of the pipe that this fluid is going through. Okay, and let's say that this fluid is going from the left to the right. Since we can't change the density of the fluid, there's no way to get the same amount of liquid through this constricted section in the middle without making it go faster. And so what we get is that as the cross-sectional area increases, the fluid slows down, and as the cross-sectional area increases, the fluid speeds up. And this equation has the form that at any two instants, the cross-sectional area times the speed is equal to the cross-sectional area times the speed at any other instant. So that's the continuity equation. Okay, let me give an example. So let's think about blood circulating through the body. Blood leaves the heart through the aorta, the main blood vessel leaving the heart. The only blood vessel leaving the heart, besides the blood that's going to be oxygenated in the lungs. So all the blood that's going to be circulated throughout the body goes through the aorta. And as it goes through the aorta, it has a speed of about 0.175 meters per second. Given that the aorta has a radius of 9 millimeters, so its diameter is 18 millimeters, 1.8 centimeters. Let's calculate what's the blood speed through capillaries, the smallest type of blood vessel that's distributing oxygen in the organs and throughout the body. So what's the blood speed in the capillaries? Now these capillaries are tiny, but there are so many of them that the effect is that the total cross-sectional area in the capillaries throughout the body is 400 times the cross-sectional area in the aorta. Okay, so the capillaries are tiny, but there's tons of them, and so they add up to a big cross-sectional area. And so what's the blood speed in the capillaries, given that the total capillary cross-sectional area is about 400 times the cross-sectional area of the aorta. Well, since we're going from a smaller cross-sectional area to a larger cross-sectional area, we expect that the speed of the blood is going to slow down in the capillaries. So first we have to calculate the area of the aorta. We're going to assume this is a circular cross-section, so this is pi r squared. So pi times 0.09 meters squared gives a cross-sectional area in the aorta of 2.545 times 10 to the minus fourth meters squared. And so now I'm going to use the continuity equation at the aorta. So we have the area 2.545 times 10 to the minus fourth times the speed of 0.175. And that's equal to the cross-sectional area total of the capillaries, which we know is going to be 400 times this cross-sectional area in the aorta, 2.545 times 10 to the minus fourth, and then times the speed in the capillaries. And so now if you divide all this out, you get that the speed of blood going through the capillaries is about 4.4 times 10 to the minus fourth meters per second. So it's very slow, but these capillaries are also very short, and there's a lot of them, and that's how blood is transmitted to cells. The other equation that we're going to be using is the Bernoulli equation. And the Bernoulli equation is applicable along any streamline, it's called. I'm not even going to write that down. But what a streamline is a path that if you were able to color a single fluid particle and follow its motion along the path, it is the path that that particle would follow, that molecule would follow. So we're talking about along the path that's traveled by any single fluid molecule and Bernoulli's equation, I'm not going to go into the derivation of this, although you can do it from Newton's second law. But it says that at one location, the pressure in the fluid plus 1/2 times the density of the fluid times the speed squared plus the height of the fluid times the density times the acceleration of gravity is equal to the same thing at any other location along this path. So this is equal to P2 plus 1/2 rho V2 squared plus Y2 rho G. And notice I didn't make a distinction between the densities at the two locations. That's because remember that we're making those four main assumptions, and one of them is that this fluid is incompressible. So the density has to be the same everywhere. So this is the Bernoulli equation, a really important equation in fluid dynamics. And this equation tells us two important things. First, it tells us how the pressure in the fluid varies with fluid speed. And second, it relates pressure and fluid speed to the fluid height. So for example, you could use this to calculate changes in blood pressure and blood speed in the head compared in the feet of a person due to the changes in height. One thing to notice about this equation is if the speed of the flow is 0, then we have fluid statics, and the Bernoulli equation reduces to our equation that from fluid statics that related the height of a fluid to its pressure. So it'll just reduce to the equation that we've used before for figuring out the pressure at a certain depth in the ocean or whatever. Okay, so the example that I'm going to give you here is going to use both the continuity equation and the Bernoulli equation. And all of the homework problems and anything on an exam and weekly assignment and everything where you're using these equations, you're going to use them both in fluid dynamics problems. Okay, so let's say that a pipe has an area of 0.01 meters squared. At the left side, and water at that location is flowing through at 4 meters per second. And we also know the pressure there, and so the pressure is equal to 1.15 times 10 to the 5th pascals. And the pipe does this. So it starts out like this and then constricts. Okay, fluid is going this way through the pipe. The difference in heights so I'm figuring out the change in height that one single molecule, if you tracked it, would follow. And this is 0.2 meters. Here we know it's going 4 meters per second. Here we know that the area, the cross-sectional area, is 0.005 meters squared. And we want to calculate the fluid speed and the fluid pressure at the right end of this pipe. So that's our goal. So what are that fluid speed V and the fluid pressure P at the right end? Well, pay attention to the flow of this problem, because this is pretty much how all the homework problems and future problems that you'll see are going to develop. You're going to use both the continuity equation and the Bernoulli equation and combine those two results to get the answer to the problem you're looking for. Okay, so first I'm going to use the continuity equation to figure out the speed V. We know that the cross-sectional area on the left end times the speed on the left end is equal to the cross-sectional area on the right end times the speed on the right end. Now solve for V, and you get that V has to be 8 meters per second. Okay, that has to be true. There's no other way for this fluid to move. And so now that we have that speed, we can use that in the Bernoulli equation. And that says that at the left end, the pressure, which is 1.15 times 10 to the 5th pascals, plus 1/2 times the density. Now this is water, so remember that the density of fresh water is 1,000 kilogram per meters cubed. Seawater is a little higher. Some other bodies of water, like the Dead Sea, are higher than that. But for fresh water, this is the density, if you're near room temperature and standard atmospheric pressure. So 1/2 times the density of water times the speed squared. This is on the left side, so that's 4. Plus, and now we have the height times the density times the acceleration of gravity. Well, just like with conservation of mechanical energy, we can choose what point we're going to call our zero height. So I'm going to choose my zero height to be the height of the water at the left, which means that this term becomes 0 for the left side. And the Bernoulli equation says we can set that equal to all of this same stuff at any other instant. To us, it's going to be at this right side of this flow. So it's equal to the pressure that we're trying to calculate plus 1/2 times 1,000 times the speed squared, and the speed at the right side is 8 meters per second. We got that from the continuity equation. And then plus, now we do have a height. If the height is 0 on the left side, the height is 0.2 meters on the right side. So plus 0.2 times the density times the acceleration of gravity in free fall. And we get this equation. Now all we have to do is solve for P, and we get that the pressure at the right side of that flow is 0.89 times 10 to the 5th pascals. So the pressure in the liquid is reduced compared to the pressure on the left side of the equation and the left side of the pipe.